Hi guys, Audrey here. So we have been learning about partial fractions. Partial fractions is a method that allows us to rewrite an integral so that we can actually do it, that we can turn it into known forms. It allows us to do this particularly with rational functions. So when we have a polynomial over a polynomial, and basically what we're doing here is we're like undoing addition of fractions. So when we do addition, we find a common denominator and we combine fractions. We're trying to find a way to undo that. So I have our steps written here just as a reminder. First, we divide if necessary. We divide in the case where the degree of the numerator is greater than or equal to the degree of the denominator. Then after that, we factor the denominator, we create a partial fractions decomposition, we solve for the numerators, and we have 2 steps for doing that, and then we rewrite the integral and solve. So last class, we mainly looked at case 1. So the different cases come into play in step 3. Case 1 was when we had our denominator factored into linear factors, so only x, not x squared, not x cubed, linear factors, and they all appeared only one time. So no like x plus 2 squared or cubed, just 1x plus 2. Today what we're going to do is we're going to look at case 2. So case 2 is what happens when the denominator is a product of linear factors, some of which are repeated. So in this case, I could have not just x plus 2, but x plus 2 squared or x plus 2 cubed. The way that we're going to look at this, we're just going to start doing a problem and we're going to follow those steps. Okay, so the first thing that we're going to do is check the degree of the numerator and the degree of the denominator. We have a rational function here. So this tells us that division, partial fractions, that's where our thoughts should be going. And I can see that the highest power on top is 4, and the highest power on the bottom is 3, and 4 is indeed bigger than or equal to 3. So this tells me that I need to start off with a division. So we're going to divide here. So we're going to do polynomial long division. I'm going to take this x cubed minus x squared minus x plus 1, and I want to divide it into x to the 4th minus 2x squared plus 4x plus 1. Now remember, we always start by looking at our first terms, so that x to the 4th, and dividing it by the first term on the outside over x cubed. And that gives me an x, and that x is what goes up here. Then I multiply that x down by the polynomial we have right there. So I will have x to the 4th minus x cubed minus x squared plus x. And I am then subtracting this polynomial. So just to be clear, that x to the 4th minus x cubed minus x squared plus x came from multiplying x by that original denominator. Now I subtract x to the 4th minus x to the 4th, that's 0, negative 2x cubed plus x cubed, that leaves me with a negative x cubed here, 4x, there is no x cubed on top, my bad. So 0x cubed plus x cubed, that actually leaves me with an x cubed here. Notice that 2x squared doesn't line up with what's below it. So we want to be really, really careful about this type of thing. So I have that minus 2x squared plus x squared actually gives me a minus x squared because there was no x cubed in that top thing. So then I have 4x minus x, that gives me a plus 3x. And then 1, there is no constant, so I just have a plus 1. And we've talked about how sometimes when this happens, the fact that there is no x cubed term on top, sometimes it's useful to pretend that there is by just writing 0x cubed. And this way things will line up and you won't accidentally make the type of mistake that you saw that I almost made. Okay. So now we keep going and we do our first terms, x cubed over x cubed. So the first term of the x cubed, I wrote x cubed, minus x squared plus 3x plus 1, and then the first term of the denominator, the original denominator. I don't stop, I keep going here because the degrees are the same. I only stop when the degree of my remainder becomes smaller than the degree of the denominator. So that hasn't happened yet. Right now they're the same. So here I have plus 1, and I have x cubed minus x squared minus x plus 1, which I am subtracting. and I get x cubed minus x cubed is 0. Negative x squared plus x squared, that's 0. 3x plus x, that's 4x. And then 1 minus 1, that's 0. So my remainder down here is 4x. We stop. Even though there's still an x left over, the degree of 4x is 1. The degree of x cubed is minus x squared minus x plus 1 is 3. So that 4x has a lower degree, which means that we can stop now. That 4x is the remainder. Okay, so now remember we write the integral is equal now to the result, which is x plus 1, plus the remainder all divided by the original denominator. So this x plus 1 part is really straightforward. Those are both just known forms, simple power rules. So this is 1/2 x squared plus x plus, and now I have this thing, which is not a known form. In fact, I really don't have a way to integrate this. So I have a polynomial over a polynomial. Substitution is not going to work. The derivative of the bottom is not equal to the top. This is a great time to use partial fractions. But notice I'm only using it on this part. Okay, so we're going to follow our partial fraction step. We already did step 1. That step 1 was to divide. So let's write that. That was our step 1. Our step 2, we'll remember, is to factor the denominator. So we're going to factor the denominator here. And we're going to have to factor by grouping because it is a cubic polynomial. So we're looking for the greatest common factor of each group. X cubed minus x squared, that's going to give me an x squared. Minus x plus 1, that's going to give me a -1. So this is equal to x squared times x minus 1 times x minus 1. We see that that x minus 1 showed up on both sides, so now we can factor it out to get x1 times x squared minus 1. Be careful. We are not done factoring. This x squared minus 1 can be factored more. In fact, it's a difference of squares. So this becomes x minus 1, then x squared minus 1 is x minus 1 times x plus 1. Now, these x minus 1s occur 2 times. For partial fractions, it's going to be super, super important to combine them. And you'll see why when we redo our case 2, when we re-talk about case 2. So in other words, this is x minus 1 squared times x plus 1. And we're going to make a little note of that here. When a factor occurs more than one time, make sure to combine them. Oops. If you don't, and you're doing partial fractions, there is a high probability that you will get the wrong answer. Make sure that you combine the things. Okay, so then step 3 is to create our partial fractions decomposition. And so when I rewrite this thing, I'm going to just ignore my integral for the time being. I'm just dealing with this 4x over x cubed minus x squared minus x plus 1. Except I'm going to write now the factor denominator here, x minus 1 squared times x plus 1. Now, the thing that makes this case 2 is the fact that that x minus 1 occurs 2 times, not just 1 time. And what that means is that it gets 2 fractions all to itself. So we saw this when we first introduced partial fractions. Our case 2, we deal with it by making sure that every possible denominator occurs. And so what happens here is I'm going to have a over x minus 1 plus e over x minus 1 squared. So where did x minus 1 come from? It could have come from x minus 1 squared, but also x minus 1 is a factor of that, and we have to take that into consideration. The x plus 1 only occurs one time, so it only gets one fraction to itself. Now, notice I've used my initials, A, E, B. Remember that you can use any letters, the letters of your choice, as long as you don't use a letter more than once. You need to have every letter be unique. So it's up to you what you write up there for me. Okay, so this is my partial fractions decomposition, that x minus 1 and x minus 1 squared, separating them like that. That's what makes this a case 2. Now for our step 4, we want to solve for the numerators. And in order to do that, this is a two-step process. We're multiplying both sides by the original denominator, which means I'm just going to have 4x left over here. But this is especially important in case 2. It's easy to screw up case 2. I'm taking a over x minus 1 and multiplying it by x minus 1 squared and x plus 1. So what happens is I have a, and only one of those x minus 1s cancel out. So I have x minus 1 times x plus 1. Plus e, now here I'm doing the same thing. I'm multiplying each of these terms by x minus 1 squared times x plus 1. In this case, the x minus 1 squareds cancel out, and e is just multiplied by x plus 1. And then plus b, I'm multiplying this again by x minus 1 squared times x plus 1. Those x plus 1s cancel out, and I have just x minus 1 squared left over. Okay, so now part B says that I want to solve for my a, e, and b, and I want to do that by plugging in x values. So it's the x values of my choice, but we start with the zeros of the denominator. So when we look at how this step is written, it says plug in x values, starting with the zeros of the denominator. So we're going to start off by finding the zeros of the denominator. So I'm basically setting this denominator, x minus 1 squared times x plus 1 equal to 0. And I can see that it gives me two x values, x equals 1 and x equals negative 1. So these are the values that I am going to start with. So I'll start with x is equal to 1, and I'm plugging that x equals 1 in to the equation that I have up there. So I have 4 times 1, that gives me a 4. And this is a, 1 minus 1 is 0, so that's just times 0, plus e, 1 plus 1 is 2, and then plus b, again, 1 minus 1 is 0, so that just gives me a 0. So 4 is equal to 2e, and e is equal to 2. Now we'll move on to x is equal to negative 1. And I'll get negative 4 is equal to, again, I have a times 0, but now I also have e times 0, and b times negative 1 minus 1, that's negative 2 squared. So I get that negative 4 is equal to 4b, and b is equal to negative 1. Now what? So I've solved for e and I've solved for b, but I no longer have any zeros left in my denominator. So what do? The answer is you plug in any other value for x that you want. I already know what e is, and I already know what b is. So we're going to plug in e and b, the values that we found, and then any other x value of our choice. Let's see it happen. So in case 2, when you have finished with the zeros of the denominator, plug in the numerators you found along with any other x value of your choice. So in other words, what I'm doing here, we're going to see this happen. I'll have 4x. I haven't solved for a, so I'll have a times x minus 1 times x plus 1. I have solved for e. E is 2. So I'll have plus 2 times x plus 1. B is negative 1. So this is minus 1 times x minus 1 squared. Now I'm going to plug in any other x value of my choice. It can literally be anything. If I want to plug in 8,484, great, I can plug that in. It's going to get me the same answer no matter what x value I plug in. That said, there are intelligent choices. For example, I haven't plugged in 0 yet. 0 is going to be a super easy number to plug in. I've already plugged in 1 and negative 1, but if I hadn't, those are also super easy numbers to plug in. Pick numbers that make plugging in easy. So in this case, I'm going to pick 0 because I haven't picked it yet. X is equal to 0. And then I get 4 times 0, that's 0, is equal to a times negative 1 times 1 plus 2 times 1 minus 1, 0 minus 1 times minus 1 squared. So I get 0 is equal to negative a plus 2 minus 1 squared is positive 1, so this is minus 1. And this gives me that a is equal to 1. There we go. That's my answer. Again, I did not have to plug in 0. I could have plugged in anything else in the whole world, and I still would have gotten that a is equal to 1. I plugged in 0 because it was the simplest thing to plug in. So I could have picked any other x value not already plugged in. Okay, so step 5. That was our step 4. We solved for our numerators. Step 5 is now to go back and rewrite the integral and solve. So we already found the integral of x plus 1. So it was just this second part that we were evaluating. So I'm going to have that this equals to 1/2 x squared plus x plus a, the integral of a, which was 1, and a was over x minus 1, plus e, which is 2, and that is over x minus 1 squared, so 2 over x minus 1 squared, and then plus my b was negative 1, which I am putting over x plus 1. Negative 1 over x plus 1 dx. Now these two things right here, these are just known forms. Those are logs. This right here, we want to be careful about. That power of 2 stops this from being a natural log. It might be useful to even think of this as the integral of 2 times x minus 1 to the negative 2 dx. The derivative of the inside is just 1. So I really don't have much to do here. I'm just applying a simple power rule. So this becomes 1/2 x squared plus x plus natural log of x minus 1. I'm applying my power rule. So that's negative 2 plus 1, that's negative 1 that I'm dividing by. So that's minus 2 times x minus 1 to the negative 1 minus natural log of x plus 1 plus c. And this is my final answer. And so we're just going to make a little note here to be careful when the power in the denominator is not 1. Okay, so I'm just going to finish this integral over here just to make sure that you guys see where that x minus 1 to the negative 1 came from. So we said that when the derivative of the inside is a constant, we just have to divide by that constant. So I'll have 2 over 1, and then x minus 1, negative 2 plus 1, that gives me a negative 1. So then I have 1 over negative 1 here, and that gives me that minus 2, x minus 1 to the negative 1. And that is my final answer. We did a partial fractions, a case 2 partial fractions that involved us starting off with a division. All right, so in the next video, we will see another example. That's all for now. Bye, guys.